So first of all, I said recall, energy is the ability to do, who remembers the punchline? Work. Okay? And then this next bit don't write down, but our first definition of work was force times distance. It's on your formula sheet, which is why I said don't bother writing it down. But that was a very limited definition. There were some conditions attached. The force had to be a constant force. What if we have a changing force? And the force and the distance had to be in the same direction, although we found some workarounds to that a little bit. It only works in very limited situations. There are many situations where you have a changing force and you'd like to know that or like to work with that. Work was also the area underneath a force versus distance graph. This is where we had that trapezoidal area and you broke it up into a triangle and a rectangle. Okay. There's a much better definition of work. It's called the work energy theorem. Why is it called that? Tyler, what are the units for work? Starts with letter J. What are the units for energy? Starts with letter J. They're not the same thing, but they're very related. And here is how they are related. The best definition for work, it's triangle PE plus triangle KE. Except if you read it that way, I'll make fun of you. What's triangle and abbrev for? It's the change in potential energy plus the change in kinetic energy. And boys and girls, what's change in anything? From your formula sheet, it's the first thing on there. If you forget, it's final minus initial. So really, this is PE final minus PE initial, whatever that is, plus KE final minus KE initial, whatever that is. That's the work done in joules. That kind of works for everything, but I use it as my last resort, because if I can use the cleaner versions, it's, again, no pun intended, much less work. If you were doing your test on Monday, I would say to you, I like this question, I like this question, I like this question. Example 1, it says this: cyclist weighs 65 kilograms, her bike weighs 72 kilograms. You know what? Let's just make a note. M equals, what's 65 plus 7.2? Okay, we'll use that as our mass. If she's pedaling over level ground, how much work does it take for her to... Ooh, okay. First of all, Colton, what's this asking me to find? So 72.2? Thank you. Colton, what's this asking us to find? How much what? Okay, look up. Don't write this down. I'll say it twice because I didn't say it twice this morning and half a dozen kids wrote it down. Don't write this down. My first thought in my brain would, Colton, to be this. But then I would say, is there a force in newtons anywhere in this question? No. Is there a distance in meters anywhere? Okay. So I would try that because it's the least amount of work, writing work. My next thought would be, well, maybe they gave me a graph. What do I mean by that? Something like this. It's pretty Captain Obvious when they give you a graph. Did they give me a graph in this question, Colton? Then I would go to what we call the work energy theorem. But I think I gave it to you on your formula sheet, did I not? And I think I even called it the work energy theorem. Did I? Okay. So I would write down, Colton, work equals delta PE plus delta KE. And in this first one, we'll write out all the components, but then we'll say, look, we can take some shortcuts. But in our notes, we'll do it at least once. What's change in anything? Final minus initial, which is always tricky to say, and I know. Finus minus, I know. So it's going to end up being PE final minus PE initial plus KE final minus KE initial. I'm going to add some brackets. You don't need to, but just to show you, there's my change in potential. There's my change in kinetic with a plus sign in the middle because we're finding the total work. Okay. Do me a favor, please. Could you underline the phrase level ground? How do I calculate gravitational potential energy? 3 letters. MGH. What's going to change if there's a change in potential energy? Well, I guess M could change. I don't think that's happening here. G could change if you're going to a different planet. We do that next year. This is one of the reasons we use this, Colton. Not looking at your phone, are you? No, sorry. I thought you were. Next year, we use this when we start doing rocket science, because as you leave Earth, the 9.8 gets smaller. We can't use MGH. We've got to go something more complicated. But I think here, we're saying there has to be a change in height. What two words did we just underline? So we could actually have crossed that. I'm going to cross all of those out. There's no change in potential because our height's not changing. We're on level ground. But if there was a hill, as long as you told me how high did we start, how high did we finish, I could handle it. Next question, Gibson. What's my equation for kinetic energy? It's on your sheet, but you might have memorized it, but it's on your sheet. So this is going to become a half mv final squared minus a half m v initial squared. In this case, I can cross out one of them. Which one can I cross out in this specific case? Bonus. So for this person to increase their speed from 0 to 5, how much energy? Let's write out the numbers. It's going to be 0.5 times 72.2 times 5 squared. Josh, what'd you get? And give it to me to all the sig figs in all its glory, because we're going to compare this. Units? Nope, that would be momentum. Sorry? Yes. By the way, the most common unit mistakes is because it's a W here, what units are people tempted to go with? Watts, and because they're kind of related, it's work over time. Don't do that. Okay. I'm going to guess all of you figured out at an early age when you were riding your bike that getting going to medium speed was pretty easy. In fact, you could do it without even breathing heavy. But if you wanted to go from medium speed to a bigger speed, that's when you're a little kid and have a one-gear bike, you learned to stand on your pedals and really, really go fast. Yes? Or once you had gears, you learned, ooh, I can shift the gears. I want you to notice, Noor, how big a speed change was there from 0 to 5 in meters per second? How big a speed change is there in part B? Also, is it going to take 902.5 joules? No, it won't. The work is going to be, again, it would be change in potential plus change in kinetic. But Noor, what's the change in potential this time? Level ground. 0, right? So it's going to be a half mv final squared minus a half mv initial squared. So it's going to be 0.5 times 72.2 times 10 squared minus 0.5 times 72.2 times 5 squared. You don't get 902.2. Even though it's the same speed increase, it takes way more energy. I think you're going to get 2,707 8.5? 2708? I might be wrong. 2707.5. I carried a one wrong. Okay? In other words, once you go medium fast, to increase your speed by the same amount takes way more energy. You figure this out when you're biking. Once you're going really fast, to go just a tiny bit faster, holy smokes, more energy is required. You got to work way harder. Where is this energy coming from in this particular case? Be really obvious. The person, where's the person getting their energy from? Gerard. Yeah, this is food energy, okay? This is one of the reasons that exercise can help you lose weight. You can set up situations where you're burning more calories than your body is taking in. Well, then you'll lose weight. Oh, Gerard, how big is the increase in part C? How many meters per second are we increasing by going from 10 to 15? Okay, it's the same increase, but I'm going to tell you, it's not going to be 2707. I think you can, without writing anything down, backspace on your calculator, change the 10 to a 15, change the 5 to a 10, and just give me the answer. Because it's the same repeating pattern here, yes? Gerard, how much work will it take? Sorry, YouTube. Gerard's working hard. He'll get there. Oh, you ready? Ready? What you got? Help them out, folks. What do we got?
5,000.
It's not 5,000. No. It's in the 40. What is it? Oliver, you sounded right. 41512 point. Is that right, folks? No, I don't think so. 4512.5. That sounds right. That there? Sorry, I thought it was in the 40,000s. Certainly, though, more. Yes? Okay. The faster you go, the more energy it takes to speed up. Explains why in a car you can't just step on the gas and go faster and faster and faster and faster and faster and faster and faster. Eventually, you'll reach the point where the total energy output of the engine is being used up by that speed increase, and you will not go faster. This also means that if you're someone who likes to speed, how many of you are about to drive or getting your license in the next year or so? Raise your hands. Okay? When you start paying for your own gas, you'll start to notice idiot drivers. I see them all the time on the Lougheed. The Lougheed is the classic one during rush hour. So what's the speed limit on the Lougheed here? For most of it, it's 60 when you're in town. And so most people do like 65. Okay, but there's always some idiot that comes past you at 90. And then you catch up to them at the next red light. The light changes green. They go zipping off. And then what? You catch up to them at the next red light. You can try this sometime. If you see that idiot driver, just kind of mentally, I'll just continue to see how often I catch up to them. And it might be not the next red light, but 3 red lights from now, sure enough, I caught up to them. What's happening with those people? They are wasting way more energy. They're throwing away gas money because they're not getting there any faster than you because of red lights. Now, it does make sense, let's say if you're on the Coquihalla, and you know that you're not going to see a red light in 600 kilometers. And the speed limit is, I think on the Coke is 115, and you say, I'm going to go 130. Okay, you will actually save time, but also understand you're going to be burning a lot more gas money as well. But at least then you'll be getting the benefit of, I shortened my trip. The idiots on the Lougheed, they're burning the gas money, and they're not shortening their trip because of red lights. You catch up to them all the time. So don't be those people. What about? No, way more. Look at these numbers, how much they're... The same increase, this is, 5 times as much as before? Pardon me? Well, no. Then if you can actually look at going from 0 to here and staying here. You're burning way more because of that squared. Remember, it's VI squared that really, really saps your gas mileage. The difference between going, for example, 105 and driving at kilometers per hour and driving at 130 kilometers per hour, that's 25. That's roughly 1/4 increase in speed. I'll bet you it's 50% or more using more gas. Way more. Yeah. It's not a win-win. Again, it may be worth it, say on the Coquihalla, where you say, well, I can get there half an hour earlier, and it's for a job interview, so I'm going to do that. Fair enough. It's the idiots that you see them in Vancouver, you see them on the Lougheed, where there's red lights in inner city driving. I just don't understand what they're trying to accomplish. End of rant. Turn the page. Let's do a little rocket science. This is basic rocket science, and then I'll show you the more advanced version. Model rocket reaches a height of 340 meters when launched. The top speed of the rocket is 85. Ooh, Clover, what's this question asked me to find? Okay, don't write this down. My first thought would be, don't write this down, force times distance. And I might even be tempted to say, well, that looks like a distance, force. Well, we're lifting. I might be tempted to say gravity. But even if I did that, what haven't I, I circled the wrong thing. That looks like distance. What haven't I used yet? That. And so I would then say, well, is there a force versus distance graph? Be obvious. I would pivot to the work energy theorem. Change in potential, write this down, plus change in kinetic. Oh, messy writing, Mr. Duke. Kinetic. I'm going to do two steps at once. I said for the first one, we would write out everything. Now I'm going to say, hey, what is the equation for potential energy? 3 letters. What's the equation for kinetic energy? 3 things. Okay, I'm going to write this as mgh final minus mgh initial plus a half mv final squared minus a half mv initial squared. The m's don't cancel, although there's an m in everything on the right. There is no m in work, which makes sense. It should take more rocket fuel to send a bigger rocket up. Then I do my usual, are any of these 0? Where would potential energy be 0 if we were on the, are we ever on the ground? Where? Initial or final? So we can go, ha-ha! In fact, I wouldn't have even bothered writing this. I would have done that in my head and jumped straight to dropping that. Ooh! What about kinetic energy? Are we ever at rest? Yes, where? On the, ha-ha! Turns out, if you want to know how many joules of energy this model rocket motor has to supply, it's going to be mgh final plus a half mv final squared. It's going to be 0.5 times, no, not 0.5, Mr. Duke, 0.15 times 9.8 times 340 plus 0.5 times 0.15 times 85. Don't forget the squared. You should be able to type that in one line and hit equals. Let's see if Gerard gets this one this time. YouTube is wondering, who's Gerard? A really nice student. Overrated. Of all the Gerards I'm teaching this year, you are my favorite, by far. It's not even close. $1,041.7. Okay. That's for toy model rockets, except we ignored air resistance. If we were really going to do this, although, why do all rockets basically look the same shape, do you think? Okay, we want to make them as aerodynamic as possible. There'll still be some. The problem with trying to take this one cosmic is as you get further from Earth, the 9.8 changes. Put your pencils down, look up. Just to let you know what it's like, this is calculating how much rocket fuel to put something in orbit. It was, this question right here. Find how much work to put it in orbit. There's the work energy theorem. We have to tweak our equations to be cosmic to work anywhere, but you can see it ends up being about 12 lines. In fact, it's the longest question, no pun intended. It's the most amount of work that we do in Physics 12 is this question here. Now, there's always some student that says, Mr. Dewick, will you teach us how to build a Death Star? Of course I will. But that's Physics 12. See, that's called a teaser. Yeah, right? Okay. I would normally say, I like example 3, I like example 3, I like example 3. You don't need to because I'm not going to be giving you a test on this time. A car is traveling at 35 meters per second. You know what? I would underline level ground because that tells me what's the change in potential energy going to be. I'm not even going to be bothered writing it. Okay. Oliver, what's A asking me to find? Keep reading. Don't write this next bit down. My first thought would be, well, force times distance. But Oliver, do you see a force in newtons? Do you see a distance in meters? Then I wouldn't write that down. I would next say, is there a force versus distance graph, Captain Obvious? And you would say, so I would pivot now to the more cumbersome, more writing, but far more flexible work energy theorem. I'm going to write the delta PE just to let you know I thought about it, but then I'm going to say, ha-ha, level ground. Oliver, what's changing anything? It's on your green sheet, top corner. We're going to get this eventually. Okay, so it's going to end up being a half mv final squared minus a half mv initial squared. Okay. Oh, are any of these zeros? Final. Okay. Comes to a stop. What does that mean? We're going to get a negative answer. Let's just crunch our numbers on this line. It's going to be negative 0.5. The mass is 1250. V is 35. Don't forget the squared. You're probably going to get a fairly big answer. I'm thinking in the hundreds of thousands, perhaps in the millions. It's going to be big. Read me the digits. All of them, please.
7, 6, 5, 6,
Units, it's work. Good. What's the negative telling me? This is not really giving me a direction. For the car to come to a stop, Oliver, does it need to gain energy or lose energy? For it to come to a stop? It's saying you need to lose that much kinetic energy. Okay. Cool. What's B asking me to find? Okay. Maybe I could do this with F equals what? MA. Maybe I could find A, but wait a minute. What did we just find in part A? What did they give me in part B? There wouldn't by chance be a version of work that has a force and a distance in it, is there? Why, there is. So now let's pivot to that one. And can you do me a favor? Get the F by itself. So F equals, give me the equation. Yep. Yet another way to find something. You've clued in, we have many ways to find stuff from the basics. Okay, let's keep going. So it's going to be negative 765, 625 divided by, use your answer button obviously, 82. You're going to get a negative answer in this case because force is a vector. This will indicate a direction. We'll talk about that in a second. Cole, what'd you get? Read me the digits, please. 933. Is that right? 933 6.9. I'll go 933. What number will I put here if I round to this? 7. And units for force? Newtons. Now, quickly, Bunny. This negative is a directional component. Hey, if the car is traveling if the car is traveling north, what direction must the braking force be? South. That's what the negative is saying. If the car, you know what? Let's be obvious. Cole, if the car is traveling forwards, what direction must the braking force be? Backwards. Okay. So this negative is a directional component. You still have this number on your. Oh, also, Cole, follow up. What force is creating this? Which force is this? I'll give you a hint. It's the force that both helps a car accelerate in the first place and brings a car to a stop. That's why you can't drive on ice. Gas is not a force. Which force is why you can't drive on ice? Help them out, folks. Friction. You're way overcomplicating this. So everybody, let's do this. Let's put a little friction right there. Okay. So let's suppose you're a tire manufacturer. You know that you have a car of this mass. You know that you have a stopping distance of this. How sticky do you need to make your tires? Josh, what's he asking me to find?
The coefficient of friction.
Mu? Hey, what's mu? I don't know. What's mu with you? So you know what? Just for giggles, I'm going to go mu equals question mark. There isn't by chance an equation that has a mu in it somewhere, is there, Josh? On your green sheet, there is one.
U times force.
Say that again. You're right.
U times net force.
Let's get the mu by itself.
You divide.
So you're telling me mu is going to be friction divided by the normal force. It's going to be, now I'm going to write answer button. You're going to get a negative mu. We'll ignore it because mu does not have any direction, but we just have that negative that's dropping down. I don't know the normal force. Or do I? We're on level ground. I don't see any hint of things lifting up or pulling it. I think even without the free body diagram, if we just imagine it, I'm pretty sure it's going to be mg. I made these numbers up. I'm really hoping we get something in the 0.6, 0.7, 0.8 range because I wanted to make these legitimate tires. I hope we don't get something bigger than 1. Oh, is there more than one thing on the bottom? Brackets around the bottom, right? What'd you get, Josh?
0.76.
Give me 3 sig figs, please.
0.762.
0.762, round it off properly? Is that right? Units. Ready? Look up. What are the units for force? What are the units for force? So it would be newtons divided by newtons. What are the units? It's a trick question. What? Now you're seeing why they're not. Yeah, no units. They cancel out. Okay. And those are legitimate tires. Okay. Again, for this next question, I would say, I like this question, I like this question. What I'm really going to say, Colton, is way back in October, I don't know if you remember, we did an RCMP crash scene question where we figured out if somebody was speeding. But in that question, I had to have the cell phone pick up the sound of the skids. I had to give you time because you didn't know much physics. But I promised you back then, I said, we'll revisit this properly. This is how the RCMP would do it. RCMP officer is investigating an accident. Car has struck a pedestrian at a school crosswalk. There are no witnesses, which probably means the pedestrian didn't make it either. The officer measures the coefficient of friction at the accident site to be 0.65. They have a little device that they drag along the ground to do that. And they measure skid marks that are 49 meters long. Should the RCMP press charges against the driver? Aaron, when you're done yawning, what's this question asking me to find? It's not obvious. We'll have to think about it. What's this question asking me to find when it says, can we press charges? Yeah. V, which one? What's V final of every car accident ever? I know that one, so which one? Okay, let's make a little note here. How can we do this? We're going to write the most obvious equation ever. Ready? Work equals work. That has to be right. No way that can be wrong. You agree with me? But now we're going to write both versions of work. On the left-hand side, go force times distance. And on the right-hand side, let's go change in PE plus change in KE, the work energy theorem. By the way, which force, Cole? Thank you. I knew you wouldn't let me down a second time. Although I'm hurt you let me down the first. Never mind. We're good. Although this doesn't contain the phrase level ground, do you see any hint in the question of a hill or a change in height? I don't. So we're going to do this. But by the way, in real life, if there was a change in elevation, you could just measure that and include it in here. What's changing anything? So we're going to get this. Force of friction times distance equals a half m v final squared minus a half m v initial squared. Aaron, are any of these zeros? So I can cross out this. Now, here's what that means, by the way. I'm going to get a negative answer on the right. But wait a minute. On the left, are the force and the distance in opposite directions? In other words, if you're moving forward, Cole, coming back to you, which direction is the force when you're coming to a stop? So are they in opposite directions? Oliver, all of you, I'm going to argue there's technically a negative there already. And what we're really going to do, on the next line, Colton, we're just going to chuck the negatives. We're going to write this. Friction times distance equals mvi squared over 2. I didn't bother writing the 1 part of the 1/2. I just put the 2 on the bottom because that looks prettier. Colton, do you remember what are we trying to find? Okay, let's come back to that. Let's play around with the left side a little bit. Josh, friction is what times what? You just told us about 5 minutes ago on your green sheet. Okay, mu times the normal force times distance equals mvi squared over 2. I don't know the normal force. Oh, but look. Oh, wait a minute. I have to visualize. Do I know the normal force? I think in this case, I know how big it is. How big is it, Gerard? Okay, so now I can write mu mg d equals mvi squared over 2. Oh! Gerard, is there an m in this term?
Yes.
Is there an m in this term? Is there a little m in everything?
Yeah.
What does that mean? Here's what it means, by the way. This method would work whether it was a semi-truck or a little Austin Mini, or even better yet, if it was a hit and run and you don't even know what vehicle it is, you can still, while you're setting your case up, while you're searching for the vehicle, you can still calculate how fast they must have been traveling. Colton, what do you say we're trying to find? How would I get the VI by itself, folks? How will I move that 2 on the bottom over? And then that's going to be via VI squared. So, here we go. VI is going to be the square root of 2 mu g d. It's going to be the square root of 2. What's mu? I don't know. Was it 0.65? G, 9.8. D, how long were the skid marks? 49? Yeah? What do you get? I don't think it's 24.9. At least not if you know how to round off properly. If you chop off, maybe it's 24.9. But I think if you round off, isn't it 24.99 or 98? Or, you know what? Let's call it 25. Units? What is that in kilometers per hour? Can we charge this person? Okay. They were doing 89 in a school zone. If it was during school hours in particular, you could probably maybe even get a vehicular manslaughter charge. If it was after school hours, do you know of many school zones that have a speed limit of 80 kilometers or 89? So even so, it's going to be probably 50 kilometers per hour. Absolutely, we could charge this person. Notice, even if we don't even know what kind of car they drive, even if it was a hit and run, we could at least set this up. Yes?
What's the second number?
I don't know. What did you get on your calculator?
24.
I don't think you got 24. Didn't you get 24.98?
Oh.
So 25.0? So I promised you way back when that we would revisit this. Now, this is probably I was going to say an equation they would have in their accident book. It's probably done with software. Yes? Can you wait? This next one is pretty cool. Kids always talk about this, and this is what we're going to finish with. Last one. Motorcycles. My older brother drives a motorcycle. He is very cautious. I find motorcycles terrifying. When I was in high school, my best friend was actually a professional motorcycle racer. I think he was ranked second in North America. His name was Steve. He raced dirt bikes, but he also had a street bike. And so I remember him giving me a ride on his motorcycle. I sat on the back seat, and they had those little pegs that you could stand, that you could put your feet on. And after I got off of the motorcycle, I kicked the pegs up. He said, no, Kelvin, put them back down. Really? I said, put them back down. I said, why? Oh, that's so that when I wipe out, I don't wreck my motorcycle. I said, Steve, you're a professional motorcycle racer. When you wipe out, oh yeah, we all expect to have a motorcycle accident. That's why they terrify me. But anyways, people drive them. You had a question or a hand up or what? No, he raced oval track dirt bike. Oh, his was a road bike. Yeah, street bike. Yeah. So, I'm about to show you a motorcycle driver being unbelievably stupid. Really, 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 really stupid. Thankfully, he was so stupid that he posted it on social media. This happened on Vancouver Island, but it went viral, and the police were able to figure out who it was. They couldn't prove the driver, but they could prove the motorcycle, and they impounded the motorcycle. Put your pencil down, look up. Don't do this at home. Why are we seeing the sky? Dumb. How fast?
20.
Units. Is it? Look at this 70 right here. That's a 3-digit number. It's tough to tell, but that's a 3-digit number. This is miles per hour. This is 220 miles per hour. So, first thing you're going to write down, convert 220 miles per hour to meters per second. My phone says 98.4. Can you write down VI equals 98.4 meters per second? That's a football field a second. Do you think any human being can safely react to anything in that time? This is just dangerous and dumb. Okay? Now you can see a little clearer. It's definitely, it's not great resolution. This is for HD cameras, but that's definitely 3 digits next to the 70. This is the kilometers per hour. This is the miles per hour. This is stupid fast. So he's just slowed down to 100 miles per hour. That's going to be V final. So convert 100 miles per hour to meters per second. 44.7. VF, 44.7 meters per second. And here's our thought puzzle questions. Did he slow down? The obvious. So did he lose kinetic energy? Where'd that energy go? He gained height? In fact, I'm looking, this road looks pretty level to me. What? Heat. Heat. How much heat? And then just for giggles, if we time how long that took, how many watts of power? And for more giggles, hey, how many light bulbs could we run off of the wasted energy? That's what we're going to figure out. But first, we need to get the time of slowing down. I'll take questions in a second. Can you get out your smartphone stopwatches, please? Okay. He's going to slow down. Get your stopwatch ready. I'll tell you when to start, but you'll also hear the engine noise change. That's when we start to slow down, and then we'll stop when he hits 100. Are you ready? Wait for it. Start. Stop. What'd you get? 16? 16, a little higher than 16? 16? 16? So call it, because we're being very rough, let's call it 16 seconds. Okay. So we've got our data. So you're going to have to help me out. What did I say VI was? VF was 44.7, is that right? And T is 16. Okay. What's A want me to find? Energy lost. You know what? That's going to be the work done in braking. It's going to be the change in kinetic energy. I didn't add the change in potential energy because Colton, that road looked pretty level to me. Someone was wondering where that was. It was on the Island Highway in Vancouver, on Vancouver Island. Yeah. So it's going to be a half m v final squared minus a half m v initial squared. I had to make some assumptions, so I said we'll assume the mass of the motorcycle and rider is 300 kilograms. I Googled a few high-speed street bikes, found their mass in kilograms, made a rough guess, average adult, and added to it, and then I rounded off to a nice round number. It wasn't exactly 300, but close enough. We're doing some rough figures. So let's crunch this here. It's going to be 0.5 times 300 times 44.7, don't forget the squared, minus 0.5 times 300 times 98.4. Don't forget the squared. You're going to get a negative answer. What's the negative telling us? Is the motorcycle gaining energy or losing energy? Lot of energy. In fact, I think you're going to get an answer, I think, in the millions. Read me the digits, please, Mara. 1, 1,
5, 2, 6, 7, 0.
We'll give him the half joule because stupidity. Did you get 1152670.5? If you didn't, check to make sure you didn't miss a squared. It's the most common one. Okay. Well, B asks, where'd that energy go? Where did it go? Yes, lot of heat. Some sound, but the vast majority is going into heating up the brakes. So what if somehow we could bleed off that energy and turn it into useful power? Well, first of all, how many watts of power? How do we find power? Power is going to be work over time, so it's going to be your answer button divided by 16. We'll ignore the negative now, because now we're assuming that we're gaining that energy back somehow, so ignore the negative on your calculator. How many watts of power? 72042. Okay. How many 60-watt light bulbs could we light? What will I do with this number to figure that out? Okay, answer button divided by 60. How many motorcycles does it take to light a light bulb? Or how many light bulbs can we light? More than one? More than 1,000? How many? Okay. All right. Question? So, your parents drive a hybrid or an electric car or a plug? Okay? One of the reasons they're so efficient, this energy that the motorcycle lost to heat, when you're slowing down, where does that energy go? Recharging the batteries. Even if, because you can see how much energy this is, you're not going as fast as the motorcycle, but the mass of the car is much bigger, so the numbers will be comparable. Even if you can bleed like 70 or 80% of that off, huge savings. Huge. Okay, yes? I don't know. I remember this went viral about 15 years ago. You can see by the quality of the cameras before HDs. And I know the RCMP, they were able to track it to the motorcycle, but nobody admitted to driving it, so they impounded the motorcycle, but the person never got caught. We all know who it was. It was the guy owning the bike, but I wasn't driving it. Oh, what are you going to do? He's not in the picture. Yes?
I wonder if it would be possible to find records.
Sorry?
Or find records of how to be able to find that motorcycle and actually easily. Yeah, those files are online. So you just have to go way.
30 more seconds. 30 more seconds. You can cross out example 4. I'm not going to do the graphing questions. Colton, your homework is just number 1, 2, and 3. I'm skipping all the graphing ones because we're not doing a test on it.